Welcome to A-Level and AP Physics. In today's lesson, we will discuss one important past paper question on thermal physics from October-November 2021, paper 4, variant 1. I said this question is very important because we will cover some very important concepts about thermal physics in today's lesson. And those concepts are most frequently asked in past papers.
For part A, we need to define specific heat capacity. First of all, let's try to understand what is specific heat capacity. Imagine that we have unit mass of any substance. When we talk about unit mass, it simply means that we are talking about 1 kg in SI units. So unit mass in SI units simply means that 1 kg. Now imagine that if we place thermometer inside this mass, so inside this substance, and let's say the temperature of this substance, the initial temperature is 20 degrees Celsius. We want to raise this temperature by 1 degree Celsius. In order to raise this temperature by 1 degree Celsius or by 1 Kelvin, the amount of thermal energy we need to supply, that amount of thermal energy is called specific heat capacity. So this is what exactly is meant by specific heat capacity. When we talk about change in temperature, so you can say to raise temperature by 1 Kelvin. You can also say to raise temperature by 1 degree Celsius, because change in temperature in Kelvin is the same as change in temperature in degree Celsius. So we can say the amount of thermal energy required to raise temperature of substance of unit mass by 1 degree Kelvin or by 1 degree Celsius, because the change in temperature in degree Celsius is equal to change in temperature in Kelvin. Now let me show you how you can write down a proper answer. So this is how you can write down a proper answer. This question has 2 marks. If you have mentioned amount of thermal energy required, you will get 1 mark, and this is B mark. And the second mark you will get if you have mentioned about change of temperature of unit mass by 1 Kelvin or by 1 degree Celsius, you will get 2nd mark. And this question has 2 marks. For part B, one question is asking us to state an expression in terms of V, N, P and Boltzmann constant K for thermodynamic temperature of the gas. So this is quite straightforward one. PV is equal to NKT. We need to write down expression in terms of PV, N and K for temperature. So simply we can say in this case T is equal to PV over NK. So this is what we need to write down, and this question has 1 mark. So if you have written this one, you will get 1 mark, and this is B mark, means it has to be in your answer, means your answer has to be in this form. For the second part, we need to show that kinetic energy of a molecule is given by this expression. So we can simply start this one from PV is equal to 1/3 nm c square. So this is mean square speed, and m here is mass of single molecule. So this one we can write down mass of 1 molecule. So this is mass of 1 molecule. So you have to be very clear about this. We are talking about kinetic energy of a molecule, mean single molecule. N is the total number of molecules. So simply we can say N is number of molecules in the gas. So this is number of molecules in a sample. Now we need to prove that EK is equal to 3/2 kT. But we have also said that PV is equal to NKT in part 1. Now simply we need to equate these two. We can say this is 1 and this is second equation. We need to equate these two to find this expression. So now simply we can say that 1/3 nm mean square speed, this is equal to NKT, but n is common on both sides, so simply we can cancel n with n. We can also multiply this side with 3, so we also have to multiply this one by 3. So this one we can cancel here, so we left with mc square, means mass of molecule time mean square speed, and this is equal to 3 kT. Now if we divide both sides by 2. So simply we can say that this is kinetic energy of a molecule. So this is translational kinetic energy of a molecule. So simply we can replace this with Ek. So Ek is equal to 3 by 2 kT. So this is our final answer, and this is what question was asking us to derive, and this is our final answer. But one thing you need to understand is that when you calculate translational kinetic energy of a molecule, temperature has to be in Kelvin. So you have to use unit Kelvin for temperature if you need to calculate kinetic energy of any molecule. So that's all what we have to do for this question. And this question has 2 marks. The first mark you will get if you use this expression. So this is M mark. So you have to use this expression. And the second mark is answer mark. You will get if you got the right answer. For this question, we need to explain why the internal energy of the gas is equal to total kinetic energy of the molecules. Internal energy of any gas, this is equal to sum of kinetic energies of molecules. Internal energy is equal to sum of kinetic energies of molecules plus potential energies of molecules. That in case of ideal gases, there are no attractive forces between molecules. As there are no attractive forces between molecules, it simply means that there is no potential energy of molecules. So simply we can say the molecules, they do not have potential energy. So in this case, internal energy is only equal to kinetic energy of molecules. Internal energy is only equal to kinetic energy of molecules. So that's all what we have to write down. The first mark you will get in this case if you have written no attractive forces between gas molecules, you will get 1 mark, and the second mark you will get if you have mentioned that potential energy of gas molecules is equal to 0. So you will get 2 marks. Now let me show you how you can write down this answer. So this is how you can write down the answer. So first mark is no forces between gas molecules, 1 mark. Second mark, no potential energy of gas molecules. And so these are 2 B marks. So you have to mention these 2 points in your answer. For part C, it is given to us the gas in B is supplied with thermal energy Q. We need to explain with reference to first law of thermodynamics why the increase in internal energy of the gas is equal to Q. First of all, we need to understand the increase in internal energy means the change in internal energy. This is equal to Q plus work done on gas. So this is the work done on gas. But work done on gas or work done by gas, this is equal to P times delta V. If there is no change in volume, it means no work is done on gas or no work is done by gas. But in this case, in part B, it was given to us that container is sealed. That was given to us in part B. Container is sealed. It simply means that the volume of the container will not change. Container is sealed simply means delta V is equal to 0. So if delta V is equal to 0, it means that W is also equal to 0. So work done by gas is equal to 0. Work done on gas also 0. So here we can simply say that delta U in this case is equal to Q. So the increase in internal energy is only due to thermal energy, or simply you can say change in internal energy is equal to Q. So 2 points we have to mention for this one. This question has 2 marks. The first mark we have to say is that delta U is equal to Q plus W work done on gas, you will get 1 mark. Then the second mark you will get if you have mentioned that container is sealed, so work done is equal to 0. So you will get the second mark. Quite straightforward question. Let me show you the answer. This is how you can write down your answer in a proper way. So we can say increase in internal energy, or simply you can say this one is delta U, the change in internal energy, is equal to Q plus work done, and this is the work done on gas in fact. So this is work done on gas. So if you have written this point, you will get 1 mark. You can write down this equation as well. If you write down this one, you will get 1 mark. So this is our B1 mark. And the second mark, if we have mentioned that container is sealed, or you can say volume is constant, so no work done, you will get second B mark. For the second part, question is asking us to use expression in part B2 and also the information from part C1 to show that specific heat capacity C of the gas is given by this expression. Simply means that we have to derive this one. If we go back to part B2, in part B2 we have discussed that kinetic energy of a single molecule, this is equal to 3 by 2 kT, and this is kinetic energy of single molecule. That if we are talking about kinetic energy of a gas, total kinetic energy of a gas, so we have to multiply this one with number of molecules, means total kinetic energy will be equal to sum of kinetic energies of all the molecules. So we will say total kinetic energy or internal energy, that will be equal to 3 by 2 nkt. If we are talking about the change in kinetic energy, so we can rewrite this one. We can say this is 3 by 2 nk times change in temperature. But for ideal gases, we also understand that delta U mean the change in internal energy. This is equal to change in kinetic energy. So simply we can say the change in internal energy, this is equal to nk times delta T. In part C1 we have discussed that delta U is equal to Q. Now we have to use these informations to derive this formula. So first of all, we will start from Q is equal to mass of the gas times C times delta T. M is the mass of the gas. That mass of the gas we have to write down in this form, means capital M is equal to N times small m, because in the final expression we need mass of single molecule. So capital M we will replace with number of molecules times mass of single molecule. So we can say NMC delta T. But Q is equal to delta U. In part C1 we have discussed. So we can say Q is equal to delta U and this is equal to MC delta T. But delta U is equal to delta EK. So we can say delta U, this is equal to delta EK, means increase in kinetic energy, and this is equal to 3 by 2 nk delta T. Now we can write down this is equal to NMC delta T, and now simply we have to further simplify this. So you can see N is common, we can cancel with N, and in this case delta T is common on both sides, we can cancel this. So we simply left with C is equal to 3 by 2k, and here we have mass, so we will divide this one by m. Simply we can say this is equal to 3k divided by 2m. So this is specific heat capacity of gas in terms of mass of single molecule and Boltzmann constant. So this is how we can derive. This question has 2 marks, and the first mark is if we have written this expression, we will get first mark, and this is C mark. And the second mark is if you have got this right answer, and this is answer mark. For part D, it is given to us that gas is able to expand now because the volume of new container is not fixed, and we need to suggest with a reason how the specific heat capacity of the gas would compare with value in C2. For this purpose, let's start from here. Let's say for case 1 we had a container that has a fixed volume. So this container has fixed volume. So this is our case 1. In this case, to increase the internal energy, we have said that Q was only equal to delta U. Mean all the thermal energy was used to increase internal energy of the gas. But now in second case, we can write down, let's say we have this cylinder. So simply you can imagine that this cylinder, inside this cylinder we have gas, and this cylinder has not fixed volume, means the volume of this cylinder can change now. So the volume of gas is not fixed. So when we heat up this one, we give certain amount of heat Q to this one, this gas will expand. So in this case, work is done by gas. So we can say the Q, this will be equal to change in internal energy plus work done by gas, so internal energy, this is directly linked with change in temperature. So we have discussed before, delta U is equal to 3 by 2 K times delta T. Now in order to increase the same temperature, we have to give more Q, because in this case gas is also doing work, means gas will do work against atmosphere, because it is given to us the pressure remains constant. So P remains constant in this case, pressure of the gas, and that will be equal to the atmosphere. So this will go on expanding, so this gas will go on expanding. So this Q, actually if we want the same rise in temperature, Q has to be greater by this amount. So Q has to be greater by this amount. Now if we write down the formula for specific heat capacity, that is equal to Q over M times delta T. So for the same rise in temperature, this Q has to be greater, because this Q is equal to delta U plus the work done by gas. So this is equal to work done by gas. So simply you can divide this one by M times delta T. M is the mass of the gas. So this Q has to be greater. So if Q is greater, it simply means that C is greater, and in this case C is simply equal to Q over M times delta T, and Q is equal to only delta U. So that's the reason the C in this case will be smaller, this will be lower, because this Q is lower. So the new value of C will be greater. So that's all what you need to understand. These points you have to understand. If you have understanding of these points, now we can write down our final answer. And this question has 2 marks. So let me explain to you how to write the answer and how marks will be awarded. First mark will be awarded if you will say, as gas expand, gas will do work against atmosphere. So in this case you can see, when the gas is expanding, gas has to do work against atmosphere. So because there is P atmosphere that is acting on the gas, so in order for gas to expand, it has to do work against atmosphere. So you will get 1 mark. For same temperature rise, more thermal energy will be required, because for the same rise in temperature you have to give more energy, because the extra energy will be equal to work done by gas. So if Q is greater, so it means C is greater, as you can see here. So larger specific heat capacity. So you will get the second mark.